Hello, everyone, but especially Professor Itala. I know that she has been behind every small detail of us being here. So thank you very much, Professor. And so it's a pleasure also to be here in this kind of very strange and special auditorium. I think it's the first time in the history, I think, that 100 students have been fully funded to attend the Congress. I don't know of that any time, in any moment in the history, no Brazil, no Germany, no Italy, no United States, never. So something is incredible. This will be a historical meeting, thanks to Professor Itala. And we will meet then. Something.
In fact, 108.
Wow, impressive. We are truly impressed, and I cannot believe it. It's something really fantastic that you have done there. So we will have this kind of back and forth between the ages, Newton da Costa, and the young people. It's a celebration both to the age and to the young. In my presentation, two words are particularly important: perspectives and mathematics. I will be speaking mostly about mathematics, not about logic. Something especially done in that way, because I think I'm interested in the philosophy of mathematics in a large way, and logic is a part of mathematics. It's an important part. I should say the very, very small part, but since we are here all logicians, me included, we should take care about that. So we will have many perspectives, a variety. The variety, I think, will be the main word in my presentation. We are interested in algebraic varieties, in topological varieties, in differential varieties, combinatorial varieties. We are interested in logical varieties. We saw this morning the immense, fantastic possibilities of just the varieties of negation, but we have an infinity of logical varieties which are extremely interesting, and also that happens with philosophy. We have a lot of different varieties of philosophies. I will stress that strongly in this presentation, in this course, in this week. The variety of mathematics, the variety of perspectives, and the fight, the extreme fight against any kind of reductionism. We don't like reductions, we like the variety in its plain complexity, and that complexity will be very important for us. So again, since this will be my perspective, my point of view, I will be more interested in logic as a part of mathematics, as the 20th century has taught us, not logic as a foundation for mathematics, which is something a little superseded by the development of mathematical logic in the 20th century. We will not be looking much to foundations, but more to mathematics itself, and in part of that mathematical inventivity, we will have the logical varieties and the philosophical varieties. So this will be the contents of my course. Today I will present what I call some of the main polarities of mathematical thought, and from there how are derived some corresponding philosophies. Today, Professor Gomez was speaking in the first course of the importance of the dialectics and the polars. That's something that we can agree completely, and the mathematics is very much condensed around polars and tensions and mediations between the polarities. Then afterwards, in the following days, I will stress some of the resolutions of those polarities. Tomorrow, we'll talk about the main trend of mathematical philosophy in the 20th century, the analytical philosophy of mathematics, which is extremely interesting, But I will fight against analytical philosophy in a strong way in this week. But we have to learn what has been produced in a positive way from analytical philosophy in the Anglo-Saxon school. Contraposed to the analytical philosophy, we will talk about synthetic philosophy, and there the French school is particularly important, the French school of philosophy of mathematics. Then we will talk about some alternative perspectives, some names there which seem a little strange, the devils, the phantasmata, Gödel will appear behind the phantasmata and the devils, and the paraconsistency perspective of Newton da Costa in homage to him. And then finally, in the last talk, I will present some of my models on mathematical philosophy that I have been working on in the last 20 years. So this is the content for today. We will talk about pendulums, the importance of the dialectics, the polarities, the back and forth between different perspectives, not ever accepting one perspective. You need a lot of perspectives, and those perspectives are fundamental. The more perspectives, the better for you, the better for mathematics, the better for philosophy. Some of those polarities can be embodied in one hypothesis. I will say that a hypothesis in a moment afterwards. And I will present some definitions of mathematics. There are a lot of definitions of mathematics. I will present some of the most usual and basic ones. After that, I will show some of the tensions between those polarities from the point of view of philosophy, of mathematics, of logic. And we will produce the perspective of this course, the importance that we need a complex geometry in order to encompass all different perspectives. And I will, at the end of the presentation today, I will quickly present the resolutions that we will explore afterwards in the coming days. So first of all, the importance of the pendulum. Here you have the pendulum. This is the pendulum drawn by Avi Warburg. Avi Warburg, perhaps not known for all of you, but Avi Warburg is the most important German historian and art critic of the 20th century. And in particular, it's something beautiful and interesting. Warburg has been translated here at Unicamp, at the A Presenza d'Antigo, Escritos Inéditos, at Unicamp 2 or 3 years ago. You can find it in your bookshops, and it's a wonderful translation of the non-published manuscripts of Warburg. These are some of those manuscripts in which you can see the pendulum, which will be fundamental for us. You have different perspectives, and then in the back and forth between the different perspectives, there is a mediation. That mediation here, clearly drawn, is the important part. We need the polarities, but what is important really in mathematics particularly is the mediation between different contradictions or different perspectives. Here you have also a beautiful diagram of Warburg, in which you have from one idea the explosion and the many ramifications of that idea. Warburg was particularly important as an art historian and art critic, looking at the antique traditions and how those antique traditions were modified and drawn in the Renaissance. So, A Presenza d'Antigo. That is something that today also Professor Gomez was recalling as the principle of adequacy of Newton da Costa, the pragmatic principle of adequacy, in which you have the pendulum, there you have the pendulum, and on one side you have a tension to one side, the tension to another side, and if you take two pendulums, one to the other, then you get something very interesting, which is the corpus of life. the curves of life are obtained with just two pendulums, one on top of the other, and moving the two pendulums in contrary senses. So you have this idea that life, or what is the real knowledge is obtained as an integration of two different movements, at least, polarities of different movements. Those two different fundamental movements will be what I will call in the course and in the following sessions, the analytic and the synthetic are the main polarities. But what is interesting beyond that is what is happening in the middle, beyond the analytic and the synthetic. If you stay all your life in the analytic tradition, you are losing a lot. If you begin to read a little of the synthetic tradition, you are losing a lot also. You need all different perspectives, and this variety is the one that we are interested in. Some years ago, I did a course in Colombia, in my university, in which I tried to do all the semester doing mathematics just by hands, nothing more than hands, looking at my body and my hands, talking and doing gestures all the time, and talking about modern and contemporary mathematics in that way, just by hand, never using slides, never using the blackboard, just hands. Is it possible? Yes, it's possible. It's a little crazy, but it is possible. So in that effort, we rejoin what Professor Gomez was recalling us this morning, the great example of Luis Vega. Luis Vega was one of our greatest colleagues in the history of logic, and I was very happy to hear today that his book on the history of logic is well appreciated. He's really one of the greatest historians of logic of all times. And he wrote in Spanish, something which is very nice also. Not everything has to be done in English. In this back and forth, this idea of Luis Vega is that we are rooted in history. And more than that, we are rooted in our bodies. Mathematics is a construction of the human body, of the human mind. Mathematics is not something which is in the cosmos or which comes from everywhere. It's an invention of hard-working people like you, like all people who have worked around mathematics, a lot of work to produce little results. And sometimes there is a genius which produces a lot of important results that changes our perspective, that changes our lives. But mathematics is rooted in movement, in the body. So in these small gestures of the hand, I try to put some of the basic fundamental polarities of mathematics. And the one fundamental that is explained a lot of times is that mathematics is the study of space and number. Yes, that's one of the many definitions, many possible definitions. We will offer a lot of possible definitions and see how these different perspectives can be integrated together. That's the idea, produce the variety and then integrate the differentials. Not just stay on one part, but using the differentials, integrate the variety. Space number, fundamental. A good example there for all of us, if you don't know it, but I will use it, the idea beyond many of the constructions that we will do in this week, is the famous Riemann-Roch theorem. Riemann-Roch theorem is one of the greatest theorems of the 19th century and one of the greatest theorems of geometry ever, in which you have a very profound but very simple idea at the same time. You have a surface, and in that surface, there are two ways of looking at the surface. Either you stay on the surface and intrinsically you make some kind of paths on the surface, and you see how many cuts separate the surface in two or not. For example, if you are in the sphere, with one cut you separate in two. If you are in the torus, you need two cuts to separate it in two, etc. The number of cuts minus one is called the genus of the surface. So just looking at the surface and going inside the surface, then you get the idea of genus. But Riemann had this incredible idea that you can capture that by a differential harmony going beyond the surface. You take all the good and bad functions that can be represented on the surface. The good functions are called the holomorphic functions, in which you have a continuity and good differentiability on the functions. The bad functions are the meromorphic functions, in which you have singularities and poles on the surface. Riemann detected a wonderful construction. If you take the dimension of the vectorial space of the meromorphic functions minus the dimension of the vectorial space of the holomorphic functions, then you get more or less the genus. So there was a strong and deep connection between the space and number there, which has been fundamental from the 19th century to today, and will appear many times in our lectures. Riemann probably will be the kind of our very, very ideal mathematician that we want to approach a little. An infinitesimal understanding of Riemann would be very, very important for us. So the going back and forth between space and number is one of the possible ways, this connection between the space and number. But then you have this polarity which is fundamental. The fight between the continuous and the discrete. You have the continuous and or the discrete, the singularities which appear, or you can have also a very fundamental, which is the finite against the infinite. These are fundamental polarities which are constructed or going down or up. We will see afterwards in our readings in our course afterwards that some of the fundamental properties of classical logic are constructed specifically to get a grab of this fundamental polarity. But there are other ones. There are other polarities which are fundamental, the negative against the positive, beauty, fundamental beauty and truth. I think that most of the great mathematicians had this very, very clearly in mind, and probably Saron Shelah, which is clearly the most important logician of the last 40 years in the world, has always put beauty at the top of his interests. He puts beauty as a 9/10 for the constructions of mathematics, and logics, constructions of logics, models, whatever, are on a bottom 5 part of the scale. But he is the greatest logician in the last 40 years, and he's saying beauty is my drive. The possible and the necessary also are fundamental. We will be having a course on modal logics and multivariate logics, etc. The one and the many, this is the fundamental polarity of the Greeks, how beyond the differentials there is something which unites the difference. The abstract and the concrete also, that's something very fundamental for the 20th century mathematics, perhaps not for the whole history of mathematics, but for the 20th century is fundamental. And I recall you that I will be talking about 20th century mathematics. It's not fair because there are a long, magnificent tradition of mathematical philosophy coming from the Greeks, then Leibniz, Euler, Peirce, a lot of brilliant philosophers of mathematics. But I had to put in one moment what to talk, and I will be talking mainly about 20th century. So in the 20th century, the abstract becomes fundamental, and the structure against the deformation. These are some of the possible approaches that you can do just by hands. There you have just the very synthetic final expression that I tried to convey with my hands, but it can be done only moving the body, and this is a kind of homage to probably one of the greatest philosophers of mathematics of the 20th century, which is Jean Cavalier. We will be talking about Cavalier in our third session in the French school. Cavalier insisted several times that mathematics is possibly an example of the historical discipline by excellence. He insisted mathematics is an invention rooted in history, in very hard-working men and women, very difficult situations, and those are really the very important constructions for the development of mathematics. So rooted in history, rooted in our body, mathematics is not something divine, it's something very human. Those main polarities are here written in a more usual language, beyond the language of strange hands. Here you have the usual definitions of mathematics. Mathematics is the study of the varieties of the space of number, the study of potentialities of structural beauty, the study of transits or obstructions between the modalities, the mediations between the continuous and the discrete, infinity and its generations and degenerations. A very important one, the borders of negation, as Professor Marcos was beginning to explain today, an infinity of beautiful possibilities of negations. This study of the borders of negation is particularly important. The founding dialectics of the Greeks, the one against the many, the foldings and the unfoldings between the real and the ideal and the concrete and the abstract. These are one of the main trends in the philosophy of mathematics, and more of the 20th century, the structures, more like the influence of both the Hilbert School and Bourbaki, and then the movement of those structures, the deformations, the quantizations of the last 20 or 30 years in mathematics. So if you put all of this together, what is mathematics? You should not accept any one of those definitions. You have to fight against all of them. But all of them together perhaps approaches a little the idea of mathematics. Perhaps all of them together. One of them will not be good. This is what I call a Yoneda perspective, in which you have a problem, and the problem is understood through its many different perspectives and relationships. This comes from category theory, and the third session we will talk about category theory and the French school. So many perspectives, those many perspectives provide you a possibility of understanding a small part of mathematics. So we have some tensions, and those tensions can be resolved in part. Here you have some of those tensions. I am putting here what I call the philosophical tensions, the basic philosophical tensions. Inside of the circle, you have what have been the most dogmatic presentations around the 20th century, in which some of them have been extremely important, but have become something which has limited the knowledge. The most important one, perhaps, is analysis, the analytical philosophy. The analytical philosophy is extremely important perspective, but a very restricted one, we will see. Very, very restricted one, which has something to do with language, a lot with logic, but very, very little with mathematics. An analytical philosopher rarely talks about Riemann, Galois, Poincaré, Hilbert, Grothendieck. Mathematics disappears completely in the analytical perspective. And I am trying to provide a perspective on mathematics. So we will not accept the restriction to analytical philosophy, as we will not restrict the other great dogma of the last 40 years, postmodernism, in which differentiation pervades all knowledge. Everything is word, everything can happen. No, that's not true. There are hierarchies. There are reasons to differentiate things, but beyond differentiation, there is something more. And another one, which is very classical and very incisive in the 20th century, is relativization. Beyond relativization, we should expect something which goes beyond that. So beyond that, beyond those tensions, and in the inside I put a plus, because those are the tendencies which have had more strength in the 20th century. But outside, I put what should be the contrapositives of that. Beyond analysis, there should be an understanding of synthesis, which has been little understood, very little understood. Beyond differentiation, there should be integration, and beyond relativization, there should be universals. That is something very important, I think, for mathematics, extremely important for logic also, the drive for universals, in which the universals do not live anymore in the absolute. The absolute can be dead, but beyond absolutes, universals in an absolute world, there are universals in relative worlds. And those are extremely important when we talk about those in our course. So we will be trying to produce something which is beautifully captured in Spanish. Beyond razón, which is reason, which is the intelligibility, there is corazón, la corrazón, the dual of reason. In Spanish, you can say corrazón is exactly the dual of reason. It's one of the few languages in which that happens. Corazón is the heart, is the real dual of knowledge, and those can be glued together. That gluing will be fundamental for us, to glue the Kantian alternative between intelligibility and sensibility. In the Kantian perspective, they are separated, and then it is difficult to look at the conjunction of them. Instead, reason and heart, razón and sensibilidad, can be glued together. And in fact, they were glued together by an Uruguayan philosopher at the beginning of the 20th century, in which razón plus sensibilidad made razonabilidad. He is Carlos Vaz Ferreira, Uruguayan philosopher of the beginning of the 20th century, the master of Joaquín Torres Garcia, from which Joao was presenting his shirt in this morning. So there is something very interesting. There is a long tradition, Latin American tradition, of thinking in an inverse way things. These inverse ways of thinking is clear, for example, in all the heritage of Professor Costa, but it goes well beyond that. It begins at least in the middle of the 19th century. That the rationalidad of Carlos Vaz Ferreira is one of those beautiful constructions in which you are looking for what is behind the visible, the invisible. You are looking what is behind reason, the sensibility, what is behind razón, which is the corazón or corazón. Okay. So those philosophical tensions will be interesting for us, and we will try, in a sense, to put all of them together in a model. That will be the end of our course on Friday. Those tensions are also mathematical in very clear and precise ways. Beyond the usual constructions in which mathematics has been constructed using atoms, for example, the long tradition of set theory in the 20th century, beyond that, there should be something different and something more profound, perhaps. In fact, the idea of a point is something completely crazy. You have never seen a point, and you will never see a point. The only thing that you can see are neighborhoods. But points is just an invention of the human mind. And those points are, in fact, related to classical logic, but when we change classical logic, points should disappear, and we will see that they disappear in a very interesting way. Beyond types, also beyond the different types, the different levels of the construction of the architectonics, there should be something more general, more universal, which is projected onto the types. The types are injected onto the archetypes, and the archetypes are projected onto the types. That happens in mathematics a lot. The idea of variation and the invariance beyond the variation go in trying to resolve this polarity. Another one fundamental is beyond the logicization, which has been extremely important in the 20th century, and which should be a critic also for all of us. There are other things which are important, and particularly in the last 30 or 40 years in mathematics, which is a drive towards geometrization, against logicization. So those drives are very interesting, and what is important, finally, as I recall you, always in the pendulum, is not to take party of one of them, not to be only a logician, only a geometrician, but to see what happens in the middle way. Geometric logic, in fact, is possibly one of the most beautiful constructions of the 20th century. So those polarities can be mediated. Those mediations will be part of our work here. This mediation here will be particularly important for us. I think is the main technical construction that we will be using in this week, in this course, the idea of shifts. We will come to shifts in due moment, but shifts is a very profound and very simple construction of mathematics, in which you have simply two topological spaces, one base space, another space on the top, which are projected the one onto the other, and which capture the idea of locality and globality, how globality can be constructed after the gluing of the locality. We will come to that with a lot of precisions afterwards. But shifts, then, will be interesting. Yeah, and if shifts are interesting, we can say, and I think I can prove more or less that it is true, that shifts is probably the most important mathematical construction done around 1950. And its importance on logic should be important, so should be clear. So a logic of shifts should be a good alternative to the logic of atoms. And in the middle ground, we will see what happens between them, the borders of the composition of logic that Cornelio and his colleague will talk on this course, and what Marcos was talking also today, the idea of these constructions, these middle constructions. That happens in logic also. Today, we were seeing the immense variety beyond classicism. I put here one of the most important, the intuitionism, but you have this immense variety of negations, the consistent negations and all other negations that were presented this morning. And in this variety, then you have the borders which are fundamental. We are interested in the borders, in enlarging our reason. Our reason should not be restricted. We are looking against the restriction of reason. We don't want a reason restricted. We want a reason which is really full. So beyond also completeness, the good properties of classical logics, finally incompleteness is much more interesting. We will see that in due moment. And beyond the usual constructions by syntax, we should be more interested in the semantics, and beyond that, in the pragmatics of the different logics. So these different logical tensions make sense, and one can wonder if those different logical tensions will have a way of being understood and constructed in a full sense. Full sense means this, in the full sense of an expanded reason. Beyond the restricted reason, we want an expanded reason in which, for example, paraconsistency is one of the many ways to construct the expanded reason, but it is one example. There are a lot of beautiful examples which are fundamental for human thought and particularly for the philosophy of mathematics, beyond logic. We will be looking for something like this. Is it possible to produce something like this, in which you have the different polarities, you have the mediations between the different polarities, there you have them, but then you have several planes which are one on top of the other. Philosophy, logic, mathematics, they are connected between them. How can we explain and produce a model, very natural, very simple model, in which those different sheets of understanding can be connected together? Probably most of you who know Riemann know that you have a Riemann surface there. We will go to Riemann surfaces afterwards at the end of our course. But the idea is to use the tools of mathematics, particularly the tools of the geometry of mathematics, since we are interested in this part of geometrization, going against just logicization. The geometrization is very important, particularly a proto-geometry beyond logic, which should be more fundamental than logic itself. So that's the idea that logic is part of mathematics and not the inverse. So that would be done using tools of mathematics, which will be essential for us on one side, what is behind this, which are the Riemann surfaces, and on the other hand, the way of gluing together different perspectives. The different perspectives are living in different worlds. How can we connect all those different worlds? You can see that there will be paths, that there will be ramification points. So we remember the basic figure with which we began with Warburg, the ramification points. Everything was in Warburg. Warburg was a truly genius. You have to read Warburg in one moment, and since you have it here at Unicamp, that's a good opportunity. So, ramifications, fundamental for knowledge, and on those ramifications, fundamental, then we have the possibility of looking at the variety, at the same time taking care of the differentials. In each of the planes, you have the differentials, but then you produce some paths, some ramifications between the different planes, and then you begin to understand or to capture in part, because we will never understand it completely, but in part, we will begin to understand this. What is mathematics? Those are different perspectives. Those different perspectives are really clearly fundamental for our knowledge. Not accepting never any reductionism. In philosophy of mathematics, you should never accept a reduction. Mathematics is complex enough, and we want to capture that complexity. Well, there will be some main resolutions of that complexity in the 20th century. Possibly the most basic ones are the analytic against the synthetic. So analysis. Analysis is very much related to the 20th century, to analytical philosophy in the 20th century, in which you have essentially, and we will see why, it is not casual. There are profound mathematical reasons why first-order classical logic is the natural logic to understand set theory. There are theorems which explain that. The Lindstrom theorem of the 1960s, we will come back to that afterwards. But if we want to understand the full richness of set theory, particularly with the compactness theorem and the Lowenheim-Skolem theorem, then you have to do that with first-order classical logic. It's mandatory. Then there is no way to scale that. And then the analyticians in the tradition that we will see next time, tomorrow, the tradition of Russell and Wittgenstein, took great care of this tradition of first-order classical logic and insisted on the development of that possibility. That was a very important possibility. It was a beautiful perspective, very interesting, extremely rich, but it had many problems, so we will see those problems afterwards. The main problem is that it was, after a moment, beyond the founders, it became a dogma. And in mathematics, you cannot accept dogmas. In mathematics, you have the richness of possibilities. No dogma will be ever good. And particularly on foundations of mathematics, you have to look at many possibilities. In foundations, you cannot be a logicist, a formalist, or intuitionist. You have to look at all the three together and take the better of them. There was one person, probably the best logician in understand those three traditions together, which was Gödel. We will talk about the great mind of Gödel, which was at the same time an intuitionist, a logicist, and a formalist, a great mind which was able to capture the best of all traditions. Instead, the continuation, the usual continuation, the lesser minds which contributed to analytical philosophy in the 20th century became very dogmatic and insisted too much on the reduction of mathematics to supposedly logic, and with that, simply mathematics disappeared, as I was saying. The main geometers disappeared, the algebraics disappeared. You will never see a work on analytical philosophy of mathematics in which Galois is talked about. And Galois is clearly the example for all of you. It's the great genius, young genius, which changes completely a perspective. It's a pity that Galois never appears in the analytical tradition. But it's normal, because the analytical tradition is only interested in essentially first-order classical logic and its variations and set theory, in which you have this basic prefix. In analysis, you look inside, so you're interested in the decomposition and the delimitation. You're interested in the positivity of the structures. You're interested in some sense of a purifying mathematics, which is something very, very far away from real mathematics. Mathematics, the more contaminated, the better. You will see that probably in many of the courses in these 2 weeks, particularly in the course of Mundici, in which this contamination is fundamental. The fundamental idea that topology, algebra, logic live together in a strong contamination. Against that, the analytical tradition wants to purify and construct the ideal Hilbert tree. And there is, of course, a strong emphasis on language. So, but that's just one perspective. There should be a lot of others. The basic other perspective should at least reverse this polarity, at least, beginning with that, reverse this polarity. I will call that the synthetic philosophy of what would be this century, in which we have the polarity reverse. Instead of looking at theory inside elements, you look at category theory outside structures. We are interested in the outside. Instead of looking at points in classical logic, you are interested in shifts, logic of shifts. So the main contraposition of the basic polarity there would be this kind of construction of logic of shifts on category theory. This has been already begun in the 1970s with the work of Lógica, which has passed away 2 weeks ago. Lógica, one of the latest mathematicians of the last 40 years, and certainly one of the driving forces in category theory and logic theory. So it's an homage also to Lógica, this encounter. In which you change completely the perspective. Instead of looking to in, you look to the trans. Trans becomes the fundamental prefix. And this will be clear for us in all our talks. We want to go beyond the transit. We are interested in the border, in the frontier, not in the good inside, which is safe, but we are interested in the bad outside, which is not safe. That's going back and forth between the inside and the outside, and in the border will be fundamental. In which we are, instead of decomposing an element, we will be composing the elements and go beyond limits. Instead of looking to the positive properties of our structures, we will be interested in the negative structures, negative part of the structures. That has been a driving force in mathematics in the last 20 or 40 years also. Non-commutative geometry of Conch, the nonlinear logic of Girard, the non-separation of Grothendieck, many of those have been some of the important forces of the constructions in mathematics in the last 20 or 30 years. Again, beyond purity and stratification and the construction of the tree, the Hilbert tree, mathematics is interested very much in the last 30, 40 years in the relativization and quantization of the structures and what is called the Gromov cloud, in which you don't have a tree which is well formed, but we have a cloud, and in that cloud you have a lot of dense points. You have the dense point of the dense concept of space, the dense concept of numbers. On those densities are related together by many paths. That's something interesting because in the cloud, in the sky, you have liberty, and instead, in the tree, in the Hilbert tree, you have a restraint, a linguistic restraint. So this basic alternative, basic polarity, beyond analysis synthesis, produces a lot of different perspectives for the understanding of mathematics, in which mathematics at the right side is much more akin to what is happening in mathematics in the last 40, 50 years than what was happening at the beginning of the 20th century. We want to go a little beyond what was happening there and explore new paths, new perspectives. But again, if we are consistent with our approach, with our models, this is what we want. We want bulbous pendulum beyond the analytic and beyond the synthetic. What is important, what is really important in mathematics is what is happening in the middle, beyond the analytic and the synthetic. That's really important. That's what produces the most important concepts in mathematics, what is in the middle. But if you are only on the left-hand side, for example, say analysis, you will never see the whole panorama. Or if you are in the right-hand side, the synthesis, but you will never see the panorama either. You need at least to open the perspectives, so go beyond analysis. That's a mandatory thing. You cannot be an analytical philosopher today. I think it's a crazy thing. But you cannot be either a synthetic philosopher. You have to be open to all the possibilities. Is that possible? Yes, it is possible, and it is mandatory, I think, for the young people. Young people cannot be dogmatic. Young people must be revolutionary like Galois. So beyond the classical polarity between analysis and synthesis, we have different possibilities, different realities. This is what I will call the pendulum of logic and foundations, in which foundations is not understood as a basis of the architectonics, but as something which happens in the architectonics, in the construction of the architectonics, in the pendulum back and forth, in the polarities, logic appears to explain that architectonics. It is not useful and not interesting as a foundation, I think. It's interesting as a mathematical reflection of all the complexities of the world. On those, in the middle, you have the classical tradition, which has been extremely important and interesting, but we know that it is with some kind of perspective, we know that it's a poor one. There are a lot of other possibilities, which is very clear and interesting, and especially clear in the 20th century, thanks to people like Goethe, in which he studied carefully the contraposition between the intuitionistic and the classical, and he was the first to show that there are infinite logics between the intuitionistic logic and the classical logic, with a very simple construction, with the very simple Heyting algebras. Gödel, in his proverbial condensity, in one page, showed that there are infinite logics between the intuitionistic calculus and the classical logic. And then Jacob, in the great Polish school, showed that that infinity is in fact a continuum, have a continuum of logics between the intuitionistic and the classical. So you have already there this incredible variety. The variety is gigantic, but not only to the left-hand side, but also going dually to the paraconsistent perspective. So you have this dual between intuitionism and paraconsistency, which has been very well explained by Topoi, by the invention of Grothendieck. We will talk about Grothendieck a lot. He hasn't appeared yet, but he will be our hero in this week. Grothendieck, one of the greatest mathematicians of all times, and certainly one of the two greatest mathematicians of the 20th century, along with Hilbert. Grothendieck invented Topoi. I will explain that with care in our third session. And Lógica, this great logician and mathematician from the United States, simplified the construction of Lógica and showed that beyond Topoi you have a lot of logics. On one side you have logics in which in the classifier object into Topoi are Heyting algebras, or you have the dual, the co-Heyting algebras. On one side you get intuitionism, on the other side you get paraconsistency. But in the middle ground, I will insist on that, the middle ground is particularly important for me. What happens in the middle? What happens in the middle? The shift logics will explain very well what happens in the middle one between the streams. And you have this wide variety, a lot of variety, particularly here, thanks to Gödel. So we have this infinite variety that Gödel captured, and those varieties should be reflected on mathematics, and back and forth. The variety of mathematics should be reflected on the variety of logics, and the variety of logics should be reflected on the variety of mathematics, back and forth. That happens extremely well with the theory of Topoi of Groth. So beyond the usual set theory, we will be talking about topos theory, which is a generalization of the category of sets, a wide generalization of the category of sets. And something that we will be interested also then is in the back and forth. The idea that we have the pendulum, and then we have to look at the mediations in the pendulum. So we have to look at translations. So this will be done also in another of the courses here at the school, the idea of translating logics. This will be studied by the course of Carnielli and colleague. And this translation is fundamental for mathematics. Mathematics is very much related to translating things. How you translate things between the space and the number, beginning by the first fundamental example that I mentioned today, the Riemann-Roch theorem. The Riemann-Roch theorem is a translation between a differential algebraic worldview, the idea of meromorphic and holomorphic functions, and a geometric intrinsic worldview, which is the idea of the genus. Those translations are fundamental in mathematics, and many of the greatest theorems in mathematics consist in good translations between different concepts. How can you translate the different concepts? In the philosophy of mathematics, there is a polarity which we will study, which is fundamental there. Is mathematics invented or discovered? This is also a polarity which has driven a lot of ink in time. Neither of the two is correct. Both are fundamental. And Grothendieck is particularly important there. He has explained that, I think, better than anyone. The idea that mathematics is at the same time an invention and a discovery. You discover some kind of structures which are beyond you, but then you invent languages and representations to show those structures. The going back and forth between invention and discovery is fundamental for mathematics, and you cannot, again, just take one of those perspectives. You need both of them. This was clear in the figure of Grothendieck, which will be beyond all of our presentations. Grothendieck will be a phantasma beyond our presentations. And sometimes that phantom will appear explicitly, but he is always beyond us. He's always there. He is beyond all of what I will be saying. Another big person, very interesting there, is Albert Lodman, a very, very little known philosopher of mathematics on the 10th century. We will speak about him in the third session in the French school tradition. Lodman was a philosopher of mathematics brought up in the school of Bourbaki. He was friend of many of the most important Bourbaki students in the 1930s, particularly a very good friend of Jacques Herbrand, the great logician who died also very early. Lodman produced a wonderful understanding of the back and forth of knowledge in mathematics between the real and the ideal, looking particularly at the mixtures and the mediations between the real and the ideal. So these mixtures here, beyond the real and the ideal, are very much studied by Lodman. We will talk about him in a moment. So again, here we will have this polarity between mathematics. Mathematics, does it speak about the real world, or does mathematics speak about the idealities? Both are fundamental. You cannot say mathematics is applied mathematics. You cannot say mathematics is abstract mathematics. You need both of them. Both of them are fundamental. You need the ideal and the real, and any reduction will be wrong philosophically. You cannot say that mathematics talks about the ideal world. You cannot say that mathematics talks about the cosmos. Now, both of them are fundamental, and in the middle one, what's happening is the idea of mixture. Mixture. The ideas or mixtures of Lodman will be one of the driving forces of our course. So some references, some basic references about what I will be talking about. These are three of my books on the philosophy of mathematics, which may be helpful in this course as complementation of what I will be saying. First of all, the book on the other hand of the pendulum. Beyond the analytical philosophy of mathematics, say 20 years ago, it was important to produce the contraposition, the polarity. Beyond analytic, there is a synthetic part. So that synthetic philosophy of contemporary mathematics, I tried to do 20 years ago, in which I did the exercise of reading what was happening in mathematics in the period 1950s to 2000, and then to look at what were the fundamental forces beyond those constructions of contemporary mathematics. Here you can see more or less the contents of that book, in which we had especially in the book to look at some mathematicians. Not just look at the logicians, like for example, some of the logicians there were Simpson, you had Lovier, then you had Shelah, but also to look at mathematicians at large. In that mathematics at large, probably the most important person is Grothendieck. Difficult to say that there had been the most important mathematician in the last 50 or 60 years. I will try to explain part of the work of Grothendieck in the following sessions. But if you want to study that with care, then you have this book of mine, some 10 years ago, some 4 years ago. It's the first complete guide to the work of Grothendieck written in any language. It hasn't been written in English or French or Polish or whatever. And it's in Spanish, but it is available to you. Here you have the contents of the book. It's a long book, like the Gomez and Ottaviano book, 700 pages, in which you have time to study for a while, in which you can go step by step on all the Grothendieck constructions between his PhD thesis in 1949 and his last works known for the community in 1991. You go step by step on all of them. It's a self-contained book. It's in Spanish. Well, that happens. Spanish is a language, so it exists in Spanish. And finally, the last one that I mentioned here is my last book, which is called Modelos en Ejes para el Pensamiento Matemático, that translates as Shift Models for Mathematical Thought. Some of those constructions I will be explaining in the last session on Friday, in which I use systematically shifts to understand mathematical creativity on different levels, with a lot of examples of the more classical examples in mathematics, Galois, Riemann, Poincaré, Cantor, Hilbert, Grothendieck, etc. A lot of particular examples thrown out in a general perspective, in a general way. Those three books and many more references can be found in my page in academia. Those are available as PDFs. It's very easy. You Google up Zalamea Academia, you will get all these books and many other books which are available there. And as Professor Marcos was saying, also I will be making available at the end of each day, also on the academia page, the PDFs of each of our lectures. So with that, we have this basic first introduction to our course. Thank you. I try to be brief, and in general, I will try to be brief. So if you have questions, you can make also all of them. At the end, also you can also cut me in the middle of the presentation, but I think that at the end it's more natural. So if you want.
Please.
Good afternoon. I have a simple question about, do you view some role to geogrammatical reasoning in mathematics, especially in your synthetical proposal?
I didn't get it very well, the idea that mathematical reasoning in mathematics.
Diagrammatic reasoning.
Diagrammatic
reasoning.
Yes, the diagrammatic reason. Thank you very much. That's an extremely important question. And in fact, yes, we will look a lot of that. And perhaps you have seen it in my presentation, in my slides. My slides have tried to be as visual as possible, in which the diagrams are fundamental. Even if the diagram is incarnated in my hand, or if the diagram is a general diagram like the ones that I have tried to produce here, in which the diagrams for me are clearly fundamental. It's a way of understanding mathematics, and I think it's a way of approaching some of those basic ideas of the human mind, in which you have these different perspectives of mathematics, in which those varieties of space and number, these transits and obstructions of the modalities, those borders of negations, those folding and unfoldings are very visual. Those visual things are very important for the mathematician. And in fact, if you have certainly lived that in your experience, when you are near a mathematician, he always goes to the blackboard, or he begins to move, or he talks, or he makes me images or metaphors or things like that. And that's the basic way how he is thinking and inventing mathematics, through images. And then afterwards comes the language. So that's the basic hypothesis which is here in this pendulum of pragmatic reason, which refers also to the Costa's pragmatic view of his principle of adequacy, in which you have some kind of, I would say, first of all, a proto-geometry. You have first the images, first the visualization, and then afterwards, after a time, comes the language which codifies those visual moments. But this is very important, the visual spheres. So yes, diagrams are really, really important in this perspective. And in my personal approach, which comes from two great masters, one is Peirce, Charles Sanders Peirce, the great philosopher of logic and mathematics of the 19th century. I have studied for long decades Peirce, and I have studied also for long decades Grothendieck. For both of them, for Peirce and Grothendieck, the visualization is fundamental, and the diagrams are clear. In fact, Peirce had another beautiful definition of mathematics that I haven't put here, but it should be there, for example. Another beautiful definition of mathematics by Peirce. Peirce says mathematics is the logical study of diagrams. So in the visualization is really a driving force for Peirce, a driving force for Grothendieck, and since I am just a student of Peirce and Grothendieck, also for me.
Thanks.
You are the chair.
Well, I have a question. I would like to. Usually, I like to wait for the students to make questions, but I cannot resist to make a personal question for you because it is something I haven't thought since a long time ago. Of course, you are right. Grothendieck and Loffredo and Doppler's theory is great panorama of whole mathematics. But my question, a little provocative, is the following.
Right.
They cannot be the whole story about mathematics because it's hard to say that you can use Doppler's theory or category theory to find good proofs like the Fermat's theorem or the four-color theory or Ramsey's theory or combinatories, or this kind of thing. So how can you reply to this sort of provocative question?
Great. I love that idea. The idea is to be very provocative. Perhaps I was today very decent, and I shouldn't be. I should be very polemic and very provocative. And this is very nice, Professor Carnielli. This comes again to the basic hypothesis of our beginning and our course. It's all in Warburg, in the oscillation diagram of Warburg, in which there is no way that category theory will help to understand all of mathematics. It helps to understand parts of mathematics. And the same way, the analytic tradition, the study of careful, for example, proof of, the proof of Fermat theorem is a good example in which you have both traditions together. You have the analysis and the category theory together, and those together produce beautiful proofs and you understand in a profound way some concepts, like the Riemann-Roch, for example, also. We will have a lot of examples of those trends in which I would say, probably I would say in a very taxative way, but probably wrong way, but not so far away from truth, that all the main important constructions in mathematics have to be on the pendulum, have to have a side which is analytic and side which is synthetic at the same time. Both of them are extremely important. So the question is very natural, provocative, but at the same time very sound in the sense that you will never accept or the analytical or the synthetic tradition. And if you want to restrict one of them, you are losing a lot.
You are cursing. Sorry. Thanks for the great talk. I just wanted some clarification for what you meant by synthetic philosophy, because in the mathematical context, I think it's pretty clear that there is some polarity between set theoretic ways of thinking and the category theoretic ways of thinking. As some of them might say, category theory is more organizational than set theory, which is more foundational. But when we are looking at mathematics, that being clear, that doesn't make the philosophy, like the philosophical approach, different. It might be that the philosophy of the mathematics is different in the sense that the philosophical ideas are different. But we have all these analytic philosophers like Loffredo, who does the philosophy of category theory, and it's difficult to say that he's not doing analytic philosophy but something else. So I'd like to hear more about what you mean by synthetic philosophy.
Okay, great. I will devote a whole session to that. So I will be very short today because my third session will be devoted entirely to explain what is synthetic philosophy in the French tradition. But before going to that, you can have here the very short table in which I try to resume the basics of the polarity, which is here. In this basic construction, you can see that synthesis, for example, will be very interested in the relationships outside the structures and not in the internal constructions of the structure. So that's a great difference. Beyond the inside, you will be looking at the outside of the structures. This provides a lot of different philosophical questions and a lot of different philosophical perspectives. For example, synthetic philosophy will be very interested in the contamination, not in the purity of the Hilbert tradition or analytical tradition in which you wanted to, in a pure and positive way, to construct the world of mathematics, but you are interested in the contamination, in the negativity properties, in which things are not so clearly stated, in which the vagueness is fundamental. So, for example, if you go to the synthetic perspective, you will be interested in a logic of the vague, not in a logic of the clear and the purity. But if you are interested in the logic of the vague, you will be approaching again pairs. you will be approaching abduction, the construction of hypotheses, and as Professor Carnielli was telling me some days ago, there is also a very nice and natural formal approaching of vagueness and of abduction using paraconsistency. So there are a lot of perspectives in the synthetic way in which you will be beyond the usual constructive layers of the architectonics of mathematics, in which you will be, for example, very sensible to what is called the point aveugle in French, which is the blind points, in which you approach something in mathematics which is blind, in which you cannot see very well. But that blindness produces strong mathematical context. To understand that blindness is fundamental to invent mathematics. That doesn't happen in analytical philosophy because blindness is taxatively out of the question. Instead, on the synthetic perspective and on other perspectives, the blindness will be fundamental, the vagueness will be fundamental, the contamination will be fundamental. I think that in English, if you say this, that something is contaminated, that is something which is not good. For us, on the contrary, if it is contaminated, the better for mathematics. Mathematics need contamination. That's something that an analytical, or particularly an Anglo-Saxon philosopher, will never accept. And this is, I am beginning to be a little polemic. Hopefully, I will be very polemic next time.
A short one. So I wonder about what's the place of automated mathematics in this picture, because I mean it seems to me that it's a bit anthropocentric, right? And this view, in the sense that I know that, for example, math is related, of course, with creativity, but it's also a lot of computation, which it could be in principle algorithmic. And I was thinking about the four-color theorem, for example, not that we need computers to prove that kind of stuff. The combinatorics is that difficult, so to say, that we need the help of computers. And there is this literature on Coq, of proof assistance, and so on, right?
Okay, Fernando. Yes, that's a very important and very interesting, also very polemic question, in which I stand on a very particular point that I put at the beginning. My hypothesis is that mathematics is an invention of humankind. Okay? That's an hypothesis. It is certain that will change perhaps in the future. Not today, but perhaps in the future, you young people perhaps will see what will be a really hybrid between the machine and the man in 30 or 40 years. For you, it will be possibly very nice and very natural. For me, it's unthinkable. I am of the old generation, and in fact, I am living in the 19th century, more or less. I am talking about the 20th century, but my heart lies in the 19th century. I am a romantic at heart, so this kind of machine world is something which I try to escape if possible. But you are completely right. You are completely right that in this approach, I am living outside the world of the machines. In the future, the philosophy of mathematics will have to take care of the work of the machines. Possibly you will be doing that, or more other people in the audience will be doing that. I am happy not to do that. Very, very happy to go to Warburg. For me, Warburg is the ideal, or Grothendieck, or Peirce, people who were not thinking about machines.
Fernando, but I don't think that Peirce is out of this process. For Peirce, it would be acceptable and explainable. Don't you think?
Yeah.
Charles Peirce?
Yeah, yes, Itala. In fact, Peirce was certainly one of the great visionary thinkers. For Peirce, it was very natural to go beyond the anthropocentric construction that Alejandro was talking about. he was really thinking about semiotics in a very large way on the cosmos. And in fact, in many of his logical tracts, here, perhaps you know that that Peirce invented something very beautiful, which are called the existential graphs. I don't know if we were going to talk about that in some moment, but those are one of the best and most beautiful constructions of logics in the history of logic. I think it's the only construction in logic which explains at the same time with the same rules classical propositional logical, first order logic, many valued logic, with the same rules. That's something incredible. No one has done it beyond Peirce. So Peirce invented these existential graphs, which were drawn in the blackboard by the mind, by the human mind. But then he was very clear, and Itala is very precise there, that beyond our human mind, Peirce was talking about something that he called the pseudo-mind. Those pseudo-mind is very, very naturally related to the machine. So yes, Peirce was beyond that, but since I am a small follower of Peirce, I have not his vision, and I have to remain in the human spirit. So good for Peirce, bad for me.
I cannot use the microphone.
Yes. Oh,
Yes,
you speak.
yes. I have two questions, in fact, because I was expecting that the tensions one tension that we are going to talk is, for example, analysis and algebra, but I didn't see the algebra as a concept, but separated in different parts. Would you mind marking the... And the other thing is the mathematics as a language. And I was expecting to say that mathematics is not a language or it is a language.
Okay, first about the algebra. Algebra is one of those constructions of the history of civilization which is taught as a mediation, as a bridge between different approaches. So algebra does live in both of the traditions at the same time. In the analytical philosophy, it works in the usual construction of our algebraic structures, say in the way of Bourbaki. Bourbaki, you have a set with a structure, points, elements, which verify certain actions. But beyond that, you can have algebraic structures in the way of Grothendieck, which is beyond the internal construction of the structure. So algebra and topology and logics and differentials and combinatorics and machines, all different perspectives will be bridges between those different perspectives. You cannot say that algebra is either analytical or either synthetic. It's a very interesting bridge between the analytical and the synthetic from the, I would say, at left from the Bourbaki perspective, at right from the Grothendieck perspective. Perhaps you know that Grothendieck was in Bourbaki, but he had strong clashes with Bourbaki. So different ways of understanding the world. And the other question was about language. The language here is very free. We can use either the usual language, combinatorial or syntactic language, for example, which was very stressed this morning by João Marcos, or you can have a language which is completely visual, or more associated to diagrams. So you can have both the visual language or the usual syntactic language. In a sense, again, perhaps our master Peirce would say, you have signs in general, and those signs can be understood either in the usual syntactic way or using more semantical and visual approaches.
There is only one question.
All right. I mean it. So you said that set theory and first-order classical logic after Russell and Wittgenstein became an analytic dogma because of lesser minds.
Yeah.
Yes. I was very surprised to hear that because it seems to me that quite a few of the people that followed Russell and Wittgenstein did not work on set theory and they did not think that classical logic was a dogma. So, for example, Quine, at the end of Two Dogmas, says precisely that even classical logic, even the principle of classical logic could be reevaluated in the way he's suggesting. And no, the Oxford Ordinary Language movement was not a very formal movement. In fact, thinking about what to say here, it occurred to me that even the early Wittgenstein, the Wittgenstein of the Tractatus, says that set theory is completely irrelevant for mathematics. So even that, this looks like a misrepresentation even of the early Wittgenstein.
Okay.
So, but yeah.
With Wittgenstein, it happens. We will talk exactly tomorrow. I will be speaking about a little about Wittgenstein and a little about Quine. So tomorrow we will be speaking about two of them. But you are completely right. First of all, that when I was thinking about the lesser minds in the analytical philosophy tradition, I was not thinking about Quine.
Right.
Okay, and Quine was I was thinking more or less about my colleagues or whatever, which are we are very little persons, not the great minds of the 20th century. So in that sense, Quine will be one of the important persons that we will talk about. And Wittgenstein, of course, Wittgenstein is such a gigantic person that finally you can find in Wittgenstein anything that you want. He had very different perspectives, and those very different perspectives, each of them are very rich. So we will be talking a little about it.
Yeah, if I can briefly follow up, as it happens, there seems to be consensus among Tractatus historians, readers, that he rejected the set theoretical approach that Russell and Frege had to mathematics. So that's one thing that you can't make Wittgenstein say whatever you want. Everyone seems to agree that he rejected that.